next up, we're going to do something called the log function, and I'm going to explain why it's used or how we're going to use it, especially on Friday. We're going to be all about the log function. All right, now the log function has been around for a long time, and essentially what it was made to do is take very, very big numbers and make them smaller, because people didn't have calculators a couple hundred years ago, and when they were dealing with big numbers, there's issues because the calculations would be off. So they invented this log function. And so what happens is it takes a big number and makes it much smaller. And so if you have that in your calculator and say you take the log of 1, the answer will be 0. If you take the log of 10, the answer will be 1. The answer will be 2. So essentially what you can see is what the log function does is it works in multiples of 10. And essentially what you're doing is you're counting the zeros on your numbers. So see how in 100 it had 2 zeros? 1,000, it's got 3 zeros. 10,000, 4 zeros. 100,000, 5 zeros. And again, if you went to 1,000,000, it'd be 6 zeros. And what really that is doing is it takes every number and puts it to the power of 10. And then we look at what the exponent would be. So 10 to the power of 0 equals 1. So that's why we have a 0. 10 to the power of 1, well, equals 10. So the exponent of 1 is what we're looking at. And I can keep going here. Well, 10 squared is equal to 100. All right, 10 to the power of 3 is equal to 1,000. 10 to the power of 4, well, that's where I get my 10,000. And lastly, 10 to the power of 5 is equal to 100,000. All right, so again, what's happening is you can look at it a couple ways. You're counting the zeros. That's if you have a nice number like 1, 10, 100, 1,000. They're all multiples of 10. That'd work. Or you can just look at it the same way as, well, 10 to the power of what equals that number, and you're using the exponent. So again, the bottom line is here is that the log function takes big numbers and puts them down into smaller numbers, and the scale is on multiples of 10 is what you're looking at. Now, you're going to, if you go and take advanced functions in math, you're going to learn a lot about the log function. But we're just going to look at some of the practical uses and one of the kind of equation use to it. Now, what we get to, whoops, come on. This is why I'm getting a new computer today. All right, come on, man. Trying to go to the next page. All right, well, we'll get to this first. Is that the Richter scale? Now, the Richter scale is an example of what we call a logarithmic scale. Now, typically what you see with a Richter scale is here's, well, I'll let you have a look here, is that, you know, you got 2 to 2.9, you know, they happen all the time. 3 to 3.9, often felt but rarely causes damage. I know a friend of mine taught in China. They have these on a daily basis. Sometimes they don't even know it's happening unless they look at their water bottle and it's kind of shuffling around a little bit. But now look at something like a number 6 to 6.9. It's strong, can be destructive in areas about 100 miles across. But then you get to like a 7 to a 7.9, it can cause serious damage over large areas. Now, a Richter scale basically goes up to 10. Now, what I'm going to explain here is, if I get my, there we go, is that example 1 here, how many times stronger is an earthquake that is a 7 on the Richter scale compared to an earthquake with a magnitude of 3 on the Richter scale? Now, what I showed you there is basically the Richter scale goes up by 1s. And so if I was to compare a 3 and a 7, I'm going to write down the number 3. And well, of course, if we're going up by 1s, the number would be 4. Next number would be 6 or 5, and then 6, and then 7. Now, the difference here is we look at the jumps that you're making. From 3 to 4 is 1 jump. The 4 to 5 is 2, 3, and there's 4 jumps there. Now, here's the thing, is that the Richter scale, I'm not going to say that a 7 is 4 times bigger than a 3. That's not true. Because the Richter scale is logarithmic, every time you go up a level, up 1, it's 10 times stronger. So a 4 is 10 times stronger than a 3. A 5 is 10 times stronger than a 4. A 6 is 10 times stronger than a 5. And you see what I'm doing here? And so if I'm comparing a 3 to a 7, I'm going to multiply by 10 4 times. Or another way of saying that using exponents, 10 to the power of 4. And 10 to the power of 4 is actually, see if it'll allow me to do it here. There we go. Whoops. Let's get the smaller letters. 10,000. And so if I can compare a 7 to a 3, a 7 is 10,000 times stronger than a 3. And so there is a huge difference there. So if you don't realize, between say a 7 and a 6, well, if 6 causes a lot of damage, a 7 causes 10 times the damage, or is 10 times stronger. All right, so it's a logarithmic scale. Now we also have another logarithmic scale, and that is when we talk about sound. And example 2 here is how many times larger is a sound that has a loudness of 80 dBs, and for those of you, it's decibels, compared to a sound that has a loudness of 50 decibels. All right, so again, I'm going to go to my scale here, and let's go up. And so here is the decibel scale. Anybody know who it's named after? A little Canadiana for you here. Crickets, eh? You guys should have way more appreciation for this particular person because you all use them. Alexander Graham Bell, the guy who invented the telephone, right? Well, it's named after him, decibels. Now, what you can see with a decibel scale is you've got barely audible, and it goes up and up and up. See how it's going up by tens? All right, and then you get to the point where you got up here in the upper echelon here of 140 decibels. Now, the reason we don't even go past 140 decibels, because there is sound louder than that, is for us, it destroys your eardrum, blows your eardrum out. And apparently it is very, very painful. I think they can put it back together because your eardrum looks like a drum, but it's never the same. It never moves the same. It's like if you put a hammer through a drum set, you could fix it, I guess, with duct tape, but it's never going to work the same. And so that's why we never go higher than 140 because, well, we're in trouble at that point. All right. Now, again, the key part here is that the decibel scale goes up by tens. And so if I'm comparing a 50 to an 80, I got 50, but this time I'm going up to 60, and then 70, and then 80. All right, and so if I'm looking for my jumps here, there's a jump. But again, it's a logarithmic scale, so a 60 is 10 times stronger than a 50. Same pattern here, times 10 and times 10. And this time we are only multiplying by 10 3 times, which is 10 to the power of 3. And, well, that's 10 times 10 times 10, which is 1,000. And so, in this case, a 80 decibel sound is 1,000 times louder than a 50 decibel sound. And again, it's because we're dealing with a logarithmic scale. So something that might be applicable to all of you or some of you is when you go away to college or university is a key thing is to have earplugs. And what you'll see is they'll have 20 decibel earplugs, right? And they will cost like, say, let's go with $10. Now, there'll also be 30 decibel earplugs. And they might be, say, $13. Now, what I see often people do is like, well, there's 20 decibels. That's how much it's reducing the sound. Costs $10. Well, only 10 more and for $13. I don't want to pay the extra. Well, the thing is the 30 decibel earbuds or earplugs are 10 times better. All right, so you're better off spending that $3. But again, if you do not understand the decibel scale, it doesn't make any sense to you. All right, or you make a bad decision. Now, all about the log rules. Again, the log function is something you would specialize in if you took advanced functions, because there's several log rules. There's a bunch of them. There's like 10 of them, I think, somewhere in there. But we need one of the log rules, and here it is. The log of a to the power of b is equal to b times the log of a. For example, if I look at the log of 3 to the power of 9, all right? And you could follow along here with me if you have your calculator. Now, 3 to the power of 9 is a big number. In fact, it is 19,683. Oops, 683. Now, as I mentioned, if I type that into my calculator to hit log and then 19,683, what the log function again does is takes a big number and makes it smaller. In fact, it would be 4.29. Now, what that log rule is saying is I can do the same thing here, but I bring the exponent down in front. And so if I calculated 9, which is my exponent, times the log of 3, well, here's what I get. It equals 9, first of all. Then I take the log of 3. Now, 3 is a small number, right? Well, the log function will make it smaller. In fact, it'll make it 0.477. Now, if I take 0.477, again, a little bit of rounding here, guess what I get? 4.29. They're equal. So this is an important log rule. All right. Well, why do we need this log rule, right? Well, here we go. We are going to have to solve equations, and we're going to need this log rule. Now, this is a log rule that can be used in math quite a bit, especially in grade 11 math in different spots, and in grade 12 math quite a bit. And here's when you're going to use the log function. We have an equation here where it says solve for x, right? 5 to the power of x is equal to 1340. Well, we have to solve for an exponent, and that's something you probably have never done before. And so what I'm going to do is I'm going to use my log rule here. So I'm going to take the log of both sides. So I'm going to take let's see here, let's try to write this down. I'm going to take the log of both sides first because I'm solving for an exponent. All right, and I got to take the log of both sides. So there we go. There's my first step, just taking the log of both sides. Now, I'm now going to use this log rule. And here's why I'm using the log rule is I'm going to bring the x down in front. Then I've got a log of 5. The log of 5 is kind of like the sine of 30 degrees, right? That's not multiplying or anything. That 5 is stuck inside that function. All right, now I can actually take the log of 1340. And so if I type that in again, log function takes a big number, makes it smaller, and in my calculator it gets 3.13. All right, well, just like I took the log of that 1340, I can take the log of 5. And if I take the log of 5, I get 0.7. And that is equal to that 3.13. And then my last step here is to divide by my numerical coefficient here. Divide by this 0.7, because these two are multiplied by each other, the x and the 0.7. And of course, what I do to one side, I do the other here. And so those divide each other out. And my x value here ends up being 4.47. So again, the log function gives us a chance to solve for an exponent, which again, unless you take my grade 11 math class, you haven't done that yet. All right, now, B, let's try it again. Now, same thing here. First step is I'm going to solve for my exponent. So I can take the log of both sides. So I got the log of 3.5 to the power of x. All right. And again, I'm taking the log on both sides here. So 920. All right. So now on my left side, again, I'm going to use my log rule where I bring the exponent down in front. And I still have the log of 3.5 here. All right, now I can go ahead again and figure out the log of 920. And remember, sometimes you can kind of figure out if your answer is right on your calculator, because I know the log of 1,000, 3 zeros, is 3. So the log of 920 is going to be just under that. And when I type into my calculator, sure enough, it is. It's 2.96. All right, well, I'm going to take the log of 3.5. Again, it's not multiplying. It's stuck in there. It's kind of like the sine, coach, or trig functions there. And let's see here. I type into my calculator log of 3.5, and I get 0.54. And again, that equals 2.96. And just like I did over on the other side there, I'm going to divide by my numerical coefficient. All right, so I'm going to divide both sides by my 0.54. And those two divide each other out. And I get an x value of, let's see here, it's going to be 5 something. Yep, 5.48. There we go. All right, now, going to do the same thing here. We're going to step it up a little bit. And I'll show you what I mean by that is, here we go, example 4. Again, solve the following equations using the log function. And again, the reason I'm using it, the log function, is because I'm solving for an exponent. And I got this log rule that allows me to make the exponent a normal number so I can deal with it. All right, so you can see I got a fraction here in my exponent, but again, same first step. I'm going to take the log of both sides. So I'm going to try to write this fraction as nice as I can. It is a power. That's a 2 there. Sorry, folks. But I am going to take the log here of 1350. All right. Now, when I apply my log rule here, I have a fraction for an exponent. Well, I'm going to have a fraction when I bring it down to a normal number. So x is the numerator, 2 is the denominator. All right, now I still have this log 3 here. All right, the log of 1350. Again, I can type that into my calculator, and I get 3.13. All right. Now, again, just a little extra step here. Log of 3. I can figure that out. And when I type in the log of 3, because x is multiplying log of 3 and 2 is dividing right here. So when I put the log of 3 in there, I get 0.48. And again, that log of 3 is timesing x. Can't forget about my 2 in the bottom. Equals 3.13. Now, there's a few ways to go from here in terms of math skills, but I just simply put these two numbers together, the 0.48 and the 2. So I take 0.48 and I divide it by 2. Well, what's half of 0.48? 0.24 times x. Again, equals my 3.13. And lastly, now that I've got it down there, because I find this is a spot where a lot of students struggle here in red. They get stuck here, just math skills, right? I just put these two numbers together, which then allows me to divide by my numerical coefficient. Whoops, 0.24. There we go. And let's see here. I take 3.13 and I divide it by 0.24. It's going to be a bigger number, 12 something. I end up with 13.04. All right. So again, I'm going to try another one of those. Okay, a little bit different here. This one's tougher. Look at the x's in the denominator here. But again, I'm going to follow the same steps. All right. So first up, take the log of both sides. So there's my log. There's my base right there. My exponent is 12 divided by x equals, and again, I'm taking the log of both sides here. So I have the log of 550. All right, so again, when I apply my log rule here, I'm going to bring the exponent down. 12's on the top, x is on the bottom. All right, and I have my log times log of 4. All right, equals. All right, take the log of 550. 2 point something, I imagine. Let's see here. Yeah, 2.74. Because again, 100 has 2 zeros and 1,000's got 3 zeros. So I knew it had to be in the middle there somewhere. All right, now the log of 4. Let's see here. So I'm going to have 12 times the log of 4, which is 0.6. All right, and that's going to equal my 2.74. Hold on here. I still got to make sure I put my x in the bottom. All right. Now I'm going to put these two numbers together. 12 times 0.6, which is 7.2 divided by x. Again, this is a spot that people struggle with. All about math. But what you don't realize here is I got a number equaling a fraction. Now, we've had that before, and I'm going to do the same thing I did before. Now, I could have done the same thing over here. I have a number equaling a fraction. Usually, it's kind of reversed, right? But what I'm going to do is creating a fraction equaling a fraction. Because, again, I can cross multiply to solve. So I'm going to have 2.74 times x is equal to 1 times 7.2. Well, that's 7.2. All right, and then finally, again, the last step here, just dividing by my numerical coefficient, 2.74 divided by 2.74 on both sides. And then I'll finally get the value of my exponent, or the value of x, I should say. In this case, it is 2.63. Again, going to 2 decimal places. And there we go. So again, there's the log function. How we're going to solve for an exponent, because in our next classes on Friday, both of them, I believe, we are going to solve for exponents in a physics nature. But we also looked at a couple of logarithmic scales. Again, we have the Decibel Scale, named after our Canadian Alexander Graham Bell. And there's also the Richter Scale, which again goes up by ones. But again, they're both logarithmic scales because as you move through the scale, it's multiples of 10. And that's what the log function's all about, is looking at your multiples of 10. All right, so that